Good day, everyone. It's nice to have you all here. Welcome to the quantum communication speech that will be given in a few minutes. Today, the speaker would be Nitish Swami, who will be speaking on quantum communication. He is a PhD student or PhD candidate at Waterford Institute of Technology. And today, the speaking would be co-moderated by Paul Gora, Karim El-Safti, and myself, Olawale Ayoade. All right, we would like to introduce our sponsors to you. This is brought to you by Quantum AI Foundation, the Warsaw Quantum Computing Meetup. We have our website placed up here for you to visit and check the events that will be coming up in case you missed any information that's been introduced earlier. The event organizer is Paul Gora. Also, we have on our sponsor list, Alexandria Quantum Computing Meetup. This is our Facebook website. Please ensure to visit to be able to get more information on this. And the event organizer will be Karim El-Safti. Also, we have the Quantum Computing and Data Science in Toronto, Ontario, Canada. The event website is also placed up here. Please ensure to visit to be able to get information about upcoming events and so many information that you might find helpful. The event organizers are Enin Descartes and Yong Chung. Also, we have on our sponsor list, we have Brooklyn Quantum Computing Meetup. We also have the website put up. Ensure to visit this website and get adequate information for yourself. We have upcoming events that would be there. Please ensure you visit the website again. The event organizer is Matthew Ways. Also, we have the OrionX.net on our sponsor list. As well, the website is placed right up here. And then this is from the founding partner of Shanin Khan. Please ensure to visit the website for information as well. We have loads of information for you. Next is the Association Quantum. We have events coming up as well on this website, associationquantum.org. Please ensure to visit the website to get enough information. This is the founder of this association is Jeff Lowy. Also on our sponsor list, we have Q Mexico, whose coordinator is Dr. Javier Oduz, which I have the privilege to know. Please ensure to check the website as well for enough information that's been placed up for you. In addition, we have Q Egypt. Q Egypt, we have the, which is coined from Q World. The website is also up here. Please ensure to visit the website to get enough information and about events that are coming up in the future. The members are Karim El-Safti, we have Dr. Ahmed Younes and Miriam Gado. And last but not least, we have Q Poland. We have the website up as well. This is also from a branch of the Q World Corporation. And then the members of this sponsors are Paul Gora and Sebastian Zayag. All right, at this time, we welcome you all one more time for joining in. We hope to have a nice and understanding topic that would be given by Nitish Swami in a few seconds. And I would like to say welcome and have a good time. Thank you. All right, we will be handing over to the speaker of the day, Nitish Swami. Nitish Swami is a PhD candidate at Walton Institute in Ireland, and it will be speaking on the interesting topic of quantum communication, which I'm really excited to hear about. His talk would be and comprising of how we can communicate in terms of the quantum world. We give the podium to Nitish Swami to give us an interesting talk. Thank you.
Good evening, everyone. I'm very glad that you gave me this opportunity to speak on such a big stage. So myself, I've been introduced myself, Nitish Swami, and I'm a first-year PhD researcher at Walton Institute in Waterford Institute of Technology, Ireland. and I'm working towards space-based quantum key distribution links, solely focusing on optical properties of such links. So today my talk will comprise of quantum communication, the basics, and the state of the art of quantum communication. So I hope that you guys enjoyed the session. So like I mentioned, I'll be focusing on quantum communication, QKD and protocols, state of the art, quantum teleportation and swapping, quantum networks, and the future of the thing. So the first question that arises is, why are we all focusing on quantum? Like, we have classical communication, so why quantum? So the main reason of quantum is, in classical communication, like I assume most of our attendees will know, that we have bits 0 and 1, but in quantum, due to quantum properties of we can have 0 and 1 at the same point in time, which allows us to have twice the number of bits to do a certain operation, which is quite good for computing, for the future of computing. And in quantum compute and in quantum, there's one thing called no copying, which states that we cannot copy a certain bit, because if we do copy that, suppose we have a bit called a and we try to copy it, we destroy the bit a. There's no longer a bit a. There's another new state called a dash. So that's something very interesting. And another huge thing with quantum bits are they have a really small lifetime, and it's very difficult to manipulate qubits. That's why there's so many groups around the world who are focusing or researching on the topic. So why quantum communication? So there are so many reasons why one might require quantum communication. First of all, definitely it's more secure, which I will be discussing later on. Second, uh, we know that big companies like Google, IBM, Microsoft are spending billions of dollars in quantum computing, but if there is no quantum communication network, you cannot access quantum computing. You cannot have secured shared quantum computing, or you cannot do quantum computing over a cloud. And there are different other applications or use case which has been determined for quantum communication network, which includes clock synchronization, secret voting, secret sharing, and even the blockchain. So in this talk, I will be focusing solely on secure communication, as this is the field I am researching in. So I have this beautiful image or figure by Stephanie Wiener in her famous paper called Quantum Internet, a vision of road of vision ahead. So in this, we can see what we want to achieve in the end by a quantum network. We want to achieve quantum computing, a shared quantum computing, but it's still years away because the technology or the equipments required for such feat are non-existent, or they are still being developed in the labs. So at this stage, we are currently at trusted repeater networks, which is basically your quantum key distribution, and prepare and measure, which is also your quantum key distribution. There are works going on in entanglement generation in different groups, like in TU Delft and in China, in which they are working towards developing entanglement-based quantum network, which is really interesting. So quantum key distribution. Quantum key distribution is the most mature application of quantum communication. And the reason we require quantum key distribution is because the public cryptography or public key distribution uh, is at risk because of the advances in quantum computing. And some of you might have a question saying that, why are we working on this now? There are no commercially available quantum computers access to the general public. And the reason that is because there might be a case you have some secure file, and an adversary, we will call her Eve, gets access to the file, and but she cannot like open the file because it's encrypted, but she can wait for like say 10-15 years when she has access to a quantum computer, and then she might be able to decipher the file and get access to the information in the file. So quantum key distribution, the files encrypted with or the data encrypted with QKD is future proof theoretically because it's based on the fundamentals of quantum physics, which is uncertainty principle and no cloning theorem. So it basically states that, like I mentioned in previous slide, that you cannot copy a qubit or a quantum state without disturbing it or destroying it. And same is with like if you have a qubit and you want to measure its spin, you cannot measure, and you measure the spin, the qubit is destroyed. You cannot do two simultaneous measurements on a single quantum state. And so there is that. Oh, sorry. So there are different, again, QKD is divided into different protocols based on how they are measured. So they are divided into CV and DV QKD. As my research is based in DV QKD, I will be focusing on that. So, but to give you an idea of what they are, I'll just tell them you verbally. So in DV QKD or discrete variable QKD, the information is encoded in polarization or phase of a single photon. And single photon detectors are used to measure the set information in the encoded photons. And in CVQKD, the information is encoded in the quadratures of coherent states of photons. And homodyne and heterodyne detectors are used to detect the or measure the shifted keys. So in DVQKD itself, there are different QKD protocols, which starts from BB84, which was the first introduced in 1980s by Bennett et al., which is based on Heisenberg uncertainty. So I will be discussing BB84 in more detail in the coming slides. Just to give you a quick view around what different sort of protocols exist. So here's a small figure on that. So we have BB84, we have entanglement-based protocols as well, like E91, which uses Bell inequality. So let me get started on BB80 protocol. So it will take a few time explaining this. So BB80 protocol in QKD, we encode the information on different degree of freedom of a photon, right? So in BB84 protocol, we have Alice and Bob. Alice is the transmitter and Bob is the receiver. And there is an adversary called Eve, right? So Alice will randomly choose different rectilinear bases using a quantum random number generator uh, to encrypt her data, and will send it to Bob using a quantum channel. And in QKD, I forgot to mention it, QKD uses both quantum channel and a classical communication channel. So we will see how it plays out over here. So when Alice chooses her random measurement basis and sends it through a quantum channel to Bob, and Bob receives it. When Bob receives a said qubit, he measures them again in a random basis, which can be rectilinear or diagonal, using single photon detectors, which he has over here, and he notes the outcome in binary digits, zeros and ones. So after the whole process of sending information from Alice to Bob, they stop, and Alice and Bob discuss they announce their choice of basis for each bit they sent, Alice sent and Bob received on authenticated classical channel, and they match if their basis is same, and if their basis is same, they keep the bit, and else they just discard the rest of the bits in which measurement basis was different. And suppose if there is an adversary in the play, and if she tries to interrupt the signals, she will introduce some sort of error, and for and if the error is above a certain threshold, Alice and Bob will just discard all the bits they have attained and or shifted, and they will just start anew. There are a couple of problems with the simple BB84 protocol, which I will say now. So the BB84 protocol relies on two single photon sources, but there is no commercially available single photon source, which is like truly single photons. They are still in development in the labs. They are using quantum dots and so on. But in general case, right now they use weak coherent pulses from coherent pulse sources, and they attenuate the intensity of the laser to single photons. And there's a problem with that, and the problem is you cannot be sure that each pulse has only one photon. There's a chance that each pulse might have more than one photons, and that gives Eves the opportunity to gain information about the about the qubits, which is called photon number splitting attack. To overcome this sort of attack, decoy state was innovated, in which Alice will send decoy states which are of the same intensities as your signal state, and because of this, Eve cannot distinguish which is the signal state and which is the decoy state. She can have the decoy state, she could be working on that, but then it's more secure. And another problem with BB84 protocol, which is a big one, is detector side attacks, because you can never be certain that your detectors are in the hand of a trusted party. And BB84 protocol can be only used in a trusted setting, which has been the case so far in the past. To overcome this, a practical solution to side channel attacks or the detector side attacks is device independent quantum key distribution, or MDI-QKD. So MDI-QKD is measurement device independent QKD, and it is based on time reversed entanglement of signals from Alice and Bob, and the security lies uh, in the terms of violation of Bell's inequality. So Alice and Bob in this case are both transmitters. So Alice prepares her photons, Bob prepares his photons, and then they send it to Charlie. Or Charlie might be an adversary Eve. So Charlie, the whole purpose of Charlie is to just do a Bell state measurement on the incoming photons. So they know, Alice and Bob, that their photons are correlated. And then they can, after the whole transmission, they can discuss it on a classical channel, their parameters of their signals. So there are numerous reasons why MDI is now was preferred when it was first introduced. One being that it can be implemented in a star topology. As you know, single photon detectors, the good ones, which work at a telecom wavelength range 1550, are quite expensive. So in a star topology, it might be the case that we have certain number of end users, and we share the detector side or the measurement side between them. And suppose a user has to connect to another user, they just send their signals to Charlie, and in the center, and hence they are connected in a secure link. But MDI-QKD also has its flaws, and one of them being low key rates because of the attenuation in an optical fiber. So twin field QKD is, we might think of it as an advanced version of MDI-QKD, in which only one signal is required to introduce interference at Charlie. So suppose Alice will send a signal, but Bob will not. So this is called sending, not sending, TFQKD. And TFQKD is able to provide positive key rates over a distance of 500 kilometers in an optical fiber. So I will discuss the state of the art of different protocols I've mentioned. So first of all is the BB84 protocol. BB84 protocol has been worked on the most in variation with decoy state. And the biggest breakthrough, I guess, in the quantum communication world was when MESI satellite based in China demonstrated satellite to ground quantum key distribution capabilities. So in this case, uh, they use different they use BB84 protocol at 850 nanometers uh, with and they use common optics to modulate and to encode the photons with the information. And this was done over 1200 kilometers. And the reason why they were researching for a space-based links is because, as you can see in this graph below over here, the distance and the link efficiency the difference between the space-based and the telecom fiber one. So for a space-based link, most of the path of a photon is just vacuum. So there's not a lot of attenuation in the upper atmosphere. It's only in the lower atmosphere, the 20 kilometers from the surface to the stratosphere, that they face any sort of attenuation. But there's work going on that to compensate that in using deep learning and adaptive optics to overcome this. So this link was only done for in the night time, because daytime there was a lot of noise from the sunlight, and it was done at 850 nanometers, and they were able to achieve a key rate of 1.6 kilobits per second over 1200 kilometers, which is a really good in terms of quantum communication. As you can see uh, in this graph, like at 150, they have key rates of around 15 kilobits per second. So, and even at 500 kilometers, they have a decent key rate of 4.5 kilobits per second, which is quite decent. If you have a low Earth orbit, uh, if you have a LEO satellite and you want to connect the LEO satellite to the ground station, you get decent amount of keys in the link. But there are a lot of problems with said satellite link. One being that satellite, we are assuming that the satellite is trusted. What if you somehow was able to hack the satellite? That's one of the problem. And the second problem, and the major problem, is the daylight use of the of the satellite to ground or ground to satellite QKD link, which the work is going on in this, and it's still a field to research in. So, so like I mentioned, MDI QKD can be worked in untrusted settings. So there has been work to demonstrate MDI QKD in a free space link in China by Cao et al., in which they demonstrated MDI over a distance of 19.2 kilometers, and they attained key rate of 6 bits per second, which might sound very low, but it's good because MDI, most of the encoding is done in the phase of the photon, and um, and they use and they use HCN nucleus, so it's a hydrogen nucleus for phase matching of the signals from both the sources Alice and Bob, and they use adaptive optics to compensate for any phase misalign or phase mismatch in the process. MDI-QKD itself in optical fiber has been demonstrated over 400 kilometers, providing uh, a positive key rates, but they are not huge, but they are positive, which is a good thing to focus on. Another major achievement was demonstrated by a Canadian group led by Valiworthy et al., in which they demonstrated uh, in which they illustrated the same fiber usage of classical and quantum data, and they used MDI QKD for in that case. And in this case, they used 1550 nanometers for both the signal, 1550 for the classical one and 1548 nanometer wavelength for the MDI quantum one. And Wang et al. Also demonstrated the MDI usage using an integrated server in a star topology with an MDI measuring chip with an FPGA. TFQKD has been demonstrated in a real field test in China, combining three locations, and have achieved a positive key rate over 521 kilometers recently. So this is all about the quantum key distribution, but these still are prepare and measure protocols and entanglement-based protocols. But we are far from achieving a quantum network if we don't talk about quantum teleportation. So quantum teleportation works by creating pairs of entangled photons and then sending one of each pair to a sender of the data and the other to the recipient of the data. So suppose when Alice receives her entangled photon from Charlie, she lets it interact with her memory qubit or her data that holds the data she wants to transmit to Bob. This interaction changes the state of her photon, and because it is entangled with Bob's photon, the interaction instantaneously changes the state of his photon too. But Bob cannot see that unless Alice tells her the information about her bits. So, like if you see this good comic strip I found on NASA's website, so unless Alice tells Bob all the information, he won't notice that his photon has also changed in respect to the photon Alice has. Once he gets all the information, he learns his photon has also changed. So quantum teleportation and swapping is one of the most major challenges to achieve in real life because of how sensitive the system might be, and it requires a lot of hardware which is very expensive to scale. But once it is done, we can have quantum repeaters to achieve a global quantum communication network. So from Messier satellite itself, they were able to demonstrate quantum teleportation between ground and a satellite. And you can see they did it obviously in during nighttime, not during daylight, because it's because of the additional noise from the sunlight. So I'll talk about quantum networks. So why we need quantum networks? Like I mentioned, we need to achieve shared quantum computing in the future and secure communication. Hence, we need a quantum network. But quantum network itself, right now, has a lot of challenges in the face of quantum repeaters because, like I said, quantum repeaters are still from existence. They are in very early stages. So one of the solutions there is to create a quantum metropolitan area network using fiber and using a satellite link to connect between different cities, which has been demonstrated, and I will be discussing it. So I will first discuss the first ever demonstrated quantum network, which was in US by DARPA. So they had 10 nodes, and they had uh, it was a trusted network, and they achieved a key rate of 400 bps, and they used a BB84 protocol, and it was demonstrated in 2005. And they used BBN hop technology to connect uh, different nodes in the network. And after DARPA, because it was after DARPA, a group in Vienna or in Europe demonstrated the Cork quantum network, which had 6 nodes, but it had a different what do you say different protocols ranging from BB84, COW, BBM92. So they had both prepare and measure and the entanglement based protocols demonstrated in this sort of network. And they also had links, fiber links, and free space optical links in the network. And they used hop by hop process to connect different nodes with each other. And they achieved quite good key rates of, like you can see over here, 3.1 kilobits per second over 33 kilometers, which was in fiber, which was the best key rate they achieved in the process. And the other one was Tokyo quantum network, which was kind of similar to your SICOC network in Vienna. So they also had 6 nodes, and they used a mix of BB84 and BBM92 protocols, and they achieved a good decent key rate of 304 kilobits per second. But these all topological, like these networks did not had a satellite link. So China recently demonstrated an integrated quantum network, which had around 700 fiber QKD links and 2 high-speed satellite to ground links. So it was done over the years. First, they established the quantum backbone, which is the fiber network they have over here. And this particular network consists of 4 quantum metropolitan area networks, a backbone network, and a satellite link. The QMENS has the quantum metropolitan network has several challenges in terms of to be able to be compatible with topological structures that connect distributed users in a large scale, address the basic architecture, use standard QKD devices that adapt to convenient extension, maintain security against known and potential attacks. The backbone itself is a trusted relay, like the whole network, and like this network is all trusted. It's not untrusted. Every single node is a trusted player to achieve end-to-end end-to-end connection between these two links. So, sorry. So to overcome this, there has been work going on in entanglement-based quantum networks. So using entanglement instead of prepare and measure QKD protocols, one can achieve a quantum network in an untrusted setting. So over here, Joshi et al. In UK, they used BBM92 protocol to have to share bipartite entangled photons between 8 users. And they were able to have untrusted setting in this case. And communication network on a citywide scale, they were able to produce. They used a WDM wavelength division multiplexing technique with 100 gigahertz in this case. And this is from TU Delft, in which they showcase the possibility of entanglement swapping between 3 nodes, Alice, Bob, and Charlie, and this was done in nitrogen vacancy diamonds. It's a whole complicated process. So there's a possibility, in the end, there's a possibility to achieve quantum communication network in an untrusted setting. So the solutions are using entanglement-based protocols, with satellites in order to fill the void until we have access to quantum repeaters. So the basic requirement in future are the functionality of your quantum network, the accessibility of your quantum network, because there's no point if the cost of developing such network is very expensive, and the distance it is able to cover. A solution proposed by Khatri et al. Is like in this figure, you see there are so many satellites. So they use 400, they simulated that using 400 LEO satellites, you can have a global quantum coverage around the globe in conjunction with fiber networks on the ground. So with this, there's a chance for the future. So the future second generation quantum repeater network will include quantum memories as well. And over here, these yellow hexagons, they are your quantum source. And this is your Bell receiver nodes where the Bell state measurement is done. So this will be already done. You will have some qubits already over here. And suppose A and B want to connect, they just send the request to their nearest station, and they just do Bell state measurement and multiple links, like you can see, in order to be connected in a secure link. So this is what we want to achieve eventually, but the road is treacherous, as there's so many technological challenges which needs to be overcome. And with this, I say thank you, and I'm looking forward to any of the questions you might be having.
Hi, Nitin. I have a question.
Yeah.
Yeah. So what I want to ask you is, I mean, thank you for covering this nice ground for all the quantum communication. what I really want to ask you is, in your PhD, what is the novel idea that you're looking at? What is the research about? Because what we covered today is all, it's all what's already been done. So what are you looking at in particular?
So I will be focusing on using MDI QKD for a satellite-based network.
So what is the difference you're doing than what has already been done? If you could elaborate, please. Thank you.
So the difference, like I said, most of the satellite-based networks, which are from China, and the proposed networks itself, they are going to operate in a trusted setting. I mean that the satellite itself will be trusted. So what I want to achieve with my PhD research is to have untrusted link between the satellite and the ground.
Great, thank you. And what is the direction you're taking? How do you, I mean, how do you intend to proceed in that direction? What is your call at the moment?
So call of the moment will be to demonstrate such technology first on the test beds in the lab and see and run simulations if it about the key rates, and eventually talk about the topology of such network if one might be able to achieve it in the future.
So are you looking at purely from a physics point of view, or are you looking at zero trust network? Because what you're describing is essentially a zero trust network, and then trying to prove QKD in that.
So I'm looking from both perspectives, but I do want to achieve zero trust network, which is because it has not been done yet, like that I know of.
Great, thank you.
Hi, Nitish. There are some questions that have been asked by the audience, which I would like to ask you
Sure.
in response to it. One of them is that how many optical fibers are in a state of the quantum computer?
Optical fiber.
Yes. How many optical fibers are in the state of the heart of a quantum computer?
As my research in quantum communication, I don't know about the quantum computer, but this one is the state of the art as of now, 4,600 kilometer long integrated QKD network, and it has 700 fiber-based QKD links on the ground.
Oh, okay. And as a follow-up question, are there apart from these demonstrations, are there recent demonstrations as to what in particular things have been communicated over a quantum channel?
So the things they have done a video conference over quantum channels. They have shared JPEGs over quantum channels between China and Austria. So they are able to do that via satellite link.
Oh, great. So another question from the audience says that what are the supports we need from classical networks to have this satellite based communication fully secure?
So I guess we need a coexistence of both the networks. Like we can have the, like because of the topology, like I have not mentioned it in my talk.
Okay.
So the request to get to establish a quantum network can be sent by a classical channel, and then the quantum thing can come in play.
Oh, okay. So one another question is that so based on your talk, you talked about the BB84 protocol, and then you listed some other protocols that we have. So for someone who doesn't really know so much about these protocols, so the general principle are the no cloning theorem, the measurement collapse, and irreversible measurements. So do all other QKD protocols follow these principles, or this is just for BB84?
No, all other protocols follow this. Like even the MDI QKD is like they prepare the states similar to BB84 protocol, like how you prepare states in BB84 protocol, but measurement is being done differently. Like all of this is based on two principles of your quantum mechanics, which is uncertainty principle and no cloning theorem.
So these are essentially quantum properties. You go to any network, this is
Yeah.
quantum mechanics. You will have to use it regardless.
Yeah.
So another question for you is that apart from everybody talks about the quantum computing, quantum communication world, and the hype about how quantum computers might be way better than classical computers. Apart from speaking from the quantum communication channel or perspective, apart from a secure communication, what other advantage do quantum communication have over classical communication?
So like I mentioned in the beginning of the talk, like other than the quantum thing, we can do like classical physics experiment, like relativity and stuff. You can have like better positioning, like GPS, using quantum communication network and better clock synchronization across the globe. You can have quantum blockchain as well if you are interested in that.
Great. Thank you. We still look forward to more questions. We will be taking questions. If you have some of the questions, please put them on the chat and we can take them.
So people are mentioning about hybrid systems. So there's something called post-quantum cryptography, which can fill the void until you have like actual quantum computers. But there is a major flaw with PQC, that is, it's not robust against quantum algorithms.
Yeah, you missed my question. I got a question in the chat. Can you look at the question? So I look at the Elon Musk's Starlink. Will they support the possibly use the quantum networks in the future? Have you heard of the Starlink from the Elon Musk?
Starlink, yeah, I've heard of Starlink, yeah.
Do they think
So
they can use quantum network for that?
You can do it. Yeah, you can do it, but it's going to be very expensive because to get a quantum network with that kind of constellation, like, Starlink is going to be like around 40,000 satellites in low Earth orbit, right? So for a quantum, but in classical, how it works, like it bounces off from one satellite to another satellite. And like I mentioned, in quantum, you cannot copy the signal and amplify it and send it to the next satellite. You have to have some sort of quantum memory or some sort of equipments which can perform entanglement swapping between these satellites. And for that reason, the cost of establishing such constellation will go up. So there's a possible way in using satellites in different orbit, which can act as a quantum memory. Like you can have a satellite in medium Earth orbit, which can act as quantum memories, and you can dump the data over there using a LEO. Like there's still work going on, but it's a possibility to have some sort of satellite-based constellation for a quantum network.
Yeah, can you say the benefits? I mean, it seems the quantum network is really, I mean, the bandwidth is so low, right? So what's the benefits for now? I mean,
benefits, like I said, it's being discovered every now and then. There's like the benefit being obviously the secure communication. Like
what else? What else?
What else? Secure like quantum, like shared quantum computing. Like obviously, quantum computers are gonna be a reality in next 15 to 20 years. You cannot do like shared quantum computing over a cloud using classical network. It's not possible because classical network won't allow you to share qubits between each other nodes. So that's why you need a quantum network.
I would just add, on that, I think the way, so first of all, on the Starlink side, Starlink is not designed for quantum communication currently. So that's that. But then you can use some quantum properties. You can use, quantum measurement, using quantum timing and stuff. But with regards to using, cloud and classical together, I think way forward in the current generation, in the current time, is that whenever you have a requirement for a quantum workload, you transfer it over as an API to a quantum cloud-based service such as IBM or Google or or Microsoft Azure Quantum or AWS Bracket. And then you get the result back, you imbibe it back into your classical workload, and that's how you do it. For this thing, you don't need a quantum network. You can do it with your regular stuff. But again, if you want to deal with the actual qubits, then yes, you need you might need a quantum channel, if you know what I mean.
Yeah, so Nitish, another question is about how can authentication or verification of identity of satellite take part in communication? How can it be done?
So quantum key distribution is basically that you establish a private key between the parties who want to establish a network. And once the keys have been established, you can trust the path, and then you can connect with them.
Okay, yeah, so another question is about, it says that can we have a network that uses current technologies and the quantum technology?
So it's like, can we have a network with both the technologies right now?
Yes, like an hybrid technology.
Like I said, they have done this in this one. In this, they had the classical data and the quantum data traveling through the same optical fiber. So it is a possibility, like in the near future, in which one can use telecom fibers to establish a quantum network.
Okay, yeah, so a question is about, someone is asking about how zero latency is achievable over quantum computing links or quantum communication links.
For zero latency, we need quantum repeaters, but still there will be latency because one of the biggest problem in any sort of computing and communication is decoherence of the photons itself. So entanglement swapping, teleportation, repeaters will decrease the latency in a network, I assume. I cannot be so sure.
Okay. So someone is asking about how one can actually design networks that supports quantum key distribution.
So there's simulation software by TU Delft called NetSquid, in which you can draw out the topology for a QKD network. So I will suggest, if you are interested in that, you can go through the software. It's a Python package and it's free. So.
Oh, okay. Can you repeat the name of that?
NetSquid.
Okay, that's great. Someone also is asking, like, are all key exchanges expected to be replaced using quantum channel?
Like in the near future, I guess majority of the military or defense stuff, high level stuff, or the banking as well, will use a quantum key distribution to authenticate the user.
Okay, so another question is asking about how useful is it for post-quantum key exchange?
It is, I did not understand the question, sorry.
So the question says, is post-quantum key exchange not a useful standard? So how useful is post-quantum key exchange?
Post-quantum key exchange between two parties. So once you establish a secure communication, it's secure until the end of the, like, it's same as your classical thing, right? You are communicating with a person. You have RSA and stuff in classical cryptography, but a person comes with quantum computer, he hacks your data. Like right now, everything is being done with Zoom and all of this thing. Like recently, like 2 or 3 months ago in Ireland, someone hacked the HSC site, and it's a government website. So it's a necessary thing to avoid ransomware and stuff, to have post-quantum exchange, like to have the security of a quantum communication network.
Okay, so someone is asking.
There is one thing I'd like to say on that question that was asked about this post-quantum key exchange, not a useful standard. So first of all, there is no post-quantum key exchange standard currently. There's post-quantum cryptography, but it's a crypto. And that crypto is still under submission with NIST and is going through its evaluation. What that does is it protects against the superior advantage that quantum computing offers in breaking our current RSA and other PKI-based systems. But it is not a standard currently, and it is not something a different key exchange. The key exchange is still the same. There are only two kind of key exchanges, which is your Diffie-Hellman, your PKI related, and your QC based. So it is not a standard currently. Thank you.
Thank you for that. So Nitish, a question is asked about, it says, is currently quantum communication only used for quantum key distribution and not for actual data transmission?
So commercially, there are QKD kits available, but experimentally people are able, like I said, they did a video conference. So it is possible to actually transmit the data, but commercially speaking, there are QKD kits available right now, but soon it might change.
So you talked about the some of the disadvantages or the challenges in quantum communication. Can you talk a little bit more about some downsides to quantum communication?
Well, the downsides are being, like as of now, the lower transmission rates. Like if you compare, we have gigabits in classical internet, and right now the maximum ever achieved was in megabits. And like another downside is the cost of the whole network will be very expensive because of all the detectors involved in the architecture. And what else I can think of? Laying the quantum network using satellite itself has so many challenges in terms of attenuation, phase misalignment, because your photon travels it like because of the beam wandering and stuff. So there are a lot of challenges which needs to be overcome to get an actual working global quantum network.
Okay, yeah. So someone is
I had a
asking.
question.
Yes, go ahead.
Can I go? Oh yes, sir. In regards to like the no copy theorem, if we have like two qubits, one of them is say like a Kate alpha and the other is 0 Kate, and we apply a C naught from the first to the second, then we get Kate alpha in both of them. Why is this not copying?
That's a good one. One might need to jump in to help me out over here.
Could you repeat the question, please?
I wrote it in the chat.
Okay, so the person is asking about explaining about the no copying theorem, and it's more like it says if we have two qubits, one with the A ket ket A and the other with ket 0, and we apply a C naught gate on ket A and T on ket 0, then we get a ket A and a ket A. Why is this copying?
So first of all, again, one of the things to understand fundamentally is that unless you observe a quantum bit or quantum information, that information is still into its superposition state, which means that it is still in the quantum state, not in the proper sense, either 1 or 0 or a classical information. And whether you apply C naught gate or you don't apply C naught gate, or you apply any gate, yeah. So even a Hadamard gate is actually, making it superposition or otherwise. You are actually still unable to, unless you observe that information is still into its quantum state. And therefore, you don't know what information is there. So how can there be copying? You see what I'm saying? That's the simplest. I mean, I can go mathematically, but this is the simplest way to look at this problem.
We have one state and we have that exact same state and we have that in two different lines. Then like, why are we not referring to that as copying?
You don't have a state because you can only observe a state if you know what the state is. And the moment you know what the state is, you've broken the quantum bit to a classical bit.
So we can copy the superposition, we can say. The superposition has been copied, I guess.
No, we are not copying the superposition.
Like if you measure the qubit, like you wrote 0 cat and 0, once you measure it, it's 0 or 1. There's no 0 cat left or 0 bra left. That's what the person is saying.
Exactly.
Yeah, I get that. Okay, thank you.
I guess the same thing in uncertainty principle. You can either measure the momentum or the position of the actual quantum state. You cannot measure both of them at once. And if you do measure, the state is destroyed.
And the moment you measure, the important thing is the observation. The moment you observe anything, and this goes back to the old physics experiment, the two-slit experiment, where when they were passing the electron through one slit, they could when they did not observe, the electron was scattered everywhere. But when they actually when they try to observe, the electron will actually go to only one pinpoint. Is it the moment you observe something, it breaks the quantum nature of the particle.
All right. That being said, Nitish, a question here is about the quantum communication. It says that is quantum communication inherently secure enough that you can do away with encryption altogether if the entire network is quantum based?
Like even if your network is quantum based, you do need encryption of some sort, because like I said, you do have quantum network, and then you do get the what do you say, your quantum computer. And if you're not encrypting your data, your quantum computer will easily read what your data is, even if it is in quantum, like quantum state or something. But you do need encryption, right?
And so, as a follow-up to what you just said, if we do need encryption, is there a possibility of this encryption being decrypted by hacking?
No, like if you do decrypt it, you are like corrupting the data itself, right? You are disturbing the quantum states of the encoded information.
Yeah, so it sounds more like based on the general principles of no cloning, measurement collapse, irreversible measurements. Is that enough to secure the information or the data?
Like there might be always the case when someone will able to break it, but as of now, there's so many it provides future-proof information theoretically, the quantum cryptography. So now, I guess no.
If I may quickly chime in on that one. First of all, from a security perspective, you have to look at three properties of the security, which is confidentiality, integrity, and availability. And you can have confidentiality of information passing through it, but like the question was that, can you decrypt that information, and is the information going to become garbage? The moment if the information becomes garbage, then you're breaking the third principle, which is of availability. And if something is you can't use some of the information, or information becomes useless, then you've broken the second principle, which is of the integrity. You could have confidentiality, but confidentiality on itself, if you can't use that information, is slightly useless. So there might be opportunity where you may not need encryption, because the very fact that your quantum channel provide a degree of encryption by default. But if you can't recover that data later on, then that you have had an availability attack. So if your quantum network, where two parties are communicating, they're passing the information, if an adversary can literally break the communication, then there is an availability attack. And therefore, QC or whatsoever is no good. So anytime you look at the security property, you have to look at it by way of confidentiality, integrity, and availability, unless you don't want you want that information to be lost forever. But then there's no point of information being lost forever, and there's no point of a quantum channel then.
Great, thank you for that. So another question for you, Nitish, is that if every key exchange is going to be replaced by QKD eventually, do you think the attempts for PQC key exchange standardization is really useful?
Quantum network, right now, it's like far from reality. I think, no, it's not useful, in my opinion, like, because it's not quantum safe in the end. People have different opinions on this thing, but in my opinion, PQC key exchange standardization is not really useful. It's rather than having the QKD, the actual quantum encryption, which is useful.
Okay, yeah, so just as a follow-up to what you just said, do you think this generation might experience any form of quantum communication?
I think so. I mean, I will say around 2030 or like the late 20s, like we might be able to have some sort of we won't have access to everyone, but I guess big laboratories, big research centers around the globe might be able to have some sort of quantum network, because there are so many proposed studies which are to be done in the future for satellite-based quantum networks as well. Like in one of the studies in the UK, it is a proposed project called Quark. They are proposing around 43 satellites and 15 ground stations to connect each of them with each other, and all the satellites are going to be in the low Earth orbit.
Oh, thank you. So on the terms of your research, is your research experimental, or you do more of simulation?
So it's a bit of both. In the end, it will be like, I'm still in the first year, so right now it's more theoretical, but eventually it will be more experimental, in which I have to demonstrate my idea on a test bed in a lab. So yeah.
Okay, great. So someone has a question about, it says that, how do we make the initial connection in quantum channel? Do we make any classical handshake protocols?
Like I said, the initial request to establish a quantum channel is done over a classical channel. And then your quantum key management protocol comes into the play.
So another question says that, could you use a QC subchannel for intrinsic integrity over fiber along the classical communication?
Yes, you can. It's a possibility to do that. There might be a bit of crosstalk between the two channels, but it's a possibility. It has been demonstrated over 40 kilometers to have quantum and classical in the same optical fiber.
Okay, yeah, so based on the
can I ask something?
Yes,
someone was talking about like post-quantum cryptography, like what does it make it secure from quantum computers, and don't we always get a huge advantage if we use Grover's algorithm against post-quantum cryptography?
All right. Could you repeat, please?
What makes post-quantum cryptography secure against quantum computers, and don't we always get a huge advantage if we use Grover's algorithm against this post-quantum cryptography?
Like I said, post-quantum cryptography is not quantum encrypted data. It's something in between. So it's more secure than the classical, but it's not secure against quantum algorithms. But the actual quantum encrypted data is, I think that's the best I can explain.
If I may chime in very quickly on the post-quantum cryptography. So I think there was a question by, I'm looking at this, and I think also the person who was just on the call. So the question was, if every key exchange is going to be replaced by QKD eventually, do you think the attempts for PQC key exchange standardization really useful? So first of all, when you say PQC key exchange standardization, there is no such thing as PQC key exchange standardization, because currently it's not a standard. What we are talking about is post-quantum crypto, which is what PQC stands for. And what post-quantum crypto is basically a lattice-based, as well as some other various new crypto that's going to be resistant to your quantum computers using Grover's algorithm. So this is where I'm referring Grover's algorithm, because the person who was on the call just now, they mentioned Grover's algorithm. However, in order to carry out a realistic attack on a Grover's algorithm, you require numbers of qubits that are not in existence currently. And from where we are right now, it seems to me that they will not be for another 20 years or so anyway. But, I mean, the way that things are moving, it's also quite possible that, Google might come up with something that's, in 5 years' time. So the next question on that is, how safe is it to work on PQC or hybrid systems currently? Well, my view personally is that if, because what is PQC? You're essentially replacing your RSA system with PQC. So there is no harm whatsoever, but you have to choose a PQC system which is based on your performance needs, because there are many. You can go to the NIST website and you can search for this PQC. These PQC crypto have a particular performance penalty. So for example, some require X amount of memory, some require X amount of speed and whatever. So you have to look at what suits you, because otherwise you'll be paying a performance penalty. But then my view is that going future, perhaps even in just as little as 5 years' time, you will see most of the crypto replaced by PQC in order to protect the internet current infrastructure. Thank you.
I wanted to say something to that. Like one of the main securities of PQC you said was that the key is really huge, which is usually a matrix, so it's quite huge. But what if we use the classical, the older algorithms and made the keys like from 1024 to something like 10,000 or 30,000? Because essentially PQC keys are that large.
So, as Abhinandan, sorry, not Abhinandan, as Nitin just said, that PQC has nothing to do with quantum. It is actually, a classical crypto that's based on either lattice-based, which is basically, for example, in very simple terms, in a layman terms, you're looking at a molecule, you're looking at its traversal point, and you're looking at its lattice, and you're working out a key based on that. So for example, currently we use something called the elliptical curve cryptography, which is looking at an ellipse and working out the points on that. So it's something very similar. So it has nothing to do with quantum, as Nitin just said. So it doesn't matter you make it 1024 or you make it 2088 or whatever. The point is that there is a proof of concept in Grover's algorithm that demonstrates that it can be broken. So what that means is there is a possibility it can be broken. When that quantum computing power becomes available, then that can be broken. And the current mitigation against that is your PQC.
My question is, why is PQC better than just increasing the key size of the previous algorithms? Grover's is like kind of independent of the algorithm. It will sort of brute force, not exactly, but sort of. So we can always get a root n log n time.
I think this part, I think we can debate over here, but I think this is beyond the realm of quantum computing we are talking about, and I don't want to take other people's time. But you can always chat outside. But the thing is that what you're referring to, whether key size or no key size, this is outside the realm of quantum computing. This has nothing to do with quantum computing, because PQC has nothing to do with quantum computing. It is another way of generating the same crypto. From one of the person has written on the chat, Hannah has written, you can read him or her message, Hanan. It says lattice, multivariant, and psych. And these are not quantum based. As a question to Nitin, what I would like to ask him is, he did mention Bose, Bose cryptography. Are there any quantum-based cryptography actually available out there, or research what is going on? Some of them, if you could mention.
Quantum-based cryptography. I know there's a company which is like, it's a startup in the US, and I forgot its name. And they are providing some sort of quantum encryption for third parties, commercially speaking. And the research wise, I guess I have no clue about that.
Because I've been searching for something based, quantum-based encryption, but I haven't been able to find much on that currently. If you know, that's why I asked the question. Thank you for that.
Yeah, so Nitish, when you talked about the other protocols relying on BB84, are there other QKD protocols that or do you have like a preference as to which one is more or a recommendation apart from BB84, or which one supersedes BB84 in terms of like security?
So in terms of security, there are so many protocols which excels over BB84. We have E91, which is an entanglement-based protocol. We have MDI, we have TF, twin field QKD, we have phase matching QKD. So these are like the states are prepared similarly as they are prepared in a BB84 protocol, but they have additional security in different terms of it. Like there are so many attacks which can be executed on a BB84 protocol. In my personal opinion, for a future quantum network, there won't be a single protocol like initially. Rather, it will be a hybrid or an amalgamation of different protocols working together. And it is feasible to use different protocols in a network.
Okay. Yeah, so this is a question that I believe has been answered in the chat, but just to hear your opinion. It says that quantum computing breaks RSA. Can quantum computing break ECC?
I think so, yeah.
Yes. Nitin, I sent you a direct message if you can respond to me. Thank you. Bye.
Yeah, sure.
I think Adam has a question. Adam, can you unmute and ask question?
Yeah, thank you. I'm wondering what the current state of art is for our both repeaters as well as storage for quantum, direct quantum, not going to digital at all. Thank you. I appreciate any comments.
Sorry, can you please repeat it again?
Hi, I'm wondering what the current state of the technology of the science is for quantum repeaters as well as quantum storage right now. I know these are weak links.
Yeah. So these are the weak links. They are still in the initial stage. Like they are able to, like they have demonstrated for like 1 millisecond or one like in milliseconds the possibility of quantum memory like storing the data itself because of the decoherence and all of this like in the last slides I presented an experiment done in TU Delft which kind of illustrates your quantum teleportation and swapping, which will be the case in a quantum repeater structure. So it is still in its very initial stage. That's why people are leaning towards more towards satellite-based quantum links, not solely satellite-based, but a hybrid of satellite and a fiber QKD network to fill in the gap of a quantum repeater thing.
With regards to quantum storage and quantum RAM, I think you're looking at, if you've been following the Google time crystal experiment, time crystals are more likely candidate for quantum memory in particular, because the time crystal essentially is a thermodynamic violation in a way that basically fluctuates between, in time. And that's where, so you actually don't know where, what is the state of your information. And that is thereby making it a very good point for storing quantum information. So that's where, that's where that is the most likely candidate for a quantum memory.
So in other words, these are time delay based, with the time crystals being a fractal time delay concept or a time box, if you will, that's fractal.
And yes and no, because, well, I mean, this is yes and no. I mean, I think that's another debate, well, another thing on its own. But essentially, you know, it literally vibrates like a pendulum, imagine, if you want to visualize it. But instead of vibrating in a physical space, it's vibrating in time, and it's in a superposition state. It's jumping from its low energy level to a high energy level, and then jumping back to low energy level, and then jumping back to, if you want to measure this waveform, what do you actually measure so essentially it's in a superposition state, and out of that will come out your actual classical bit, whatever you want to, how you want to put your modulation on that. So that's the rough idea of it. I mean, I'm no expert in time crystal, but I've been following it, and this is my understanding of it anyway, in a very layman's term.
Thank you. Yeah, this is appreciated. I see that these are key parts of the network that are needed to really maybe even keep it in quantum without going digital, which I see as the best way to be truly unhackable. Thanks.
Powell and Deb, do you have questions or comments?
No, I think that I don't have more questions now.
I don't have either. So thank you very much.
Maybe just a comment, like this discussion about time crystals is very interesting. So indeed, it's very hot topic recently. So I think we are all excited about the future of this.
I just love everything quantum, and if it's got weird sounding words like time crystal and all, which sounds like science fiction, it excites me even more. Yes. Sorry.
Okay. Yeah. And by the way, do you maybe recommend some good sources from which we or our participants can learn more about time crystals?
I think, the funny thing is that the Google paper, or majority of the papers, are really kind of, very too technical for an average person. What I would say is that the best I read both technical paper as well as, the normal ones. I found the Forbes article, those are published. They actually distilled it down pretty nicely. They actually break it down into, something you can physically feel and see, visualize it really. And I think that's really, really good, because otherwise the papers don't do it justice. I mean, and the other thing is, I think from me, I have a base, a good physics background education. And I think if you have had some physics background, or if you can go and spend some time doing some physics, working out some basic quantum physics background, laws of thermodynamics, for example, will give you a great insight into how actually time crystals work. And also, how do, the electrons jump from one orbit to another. That'll also help understand both lattice-based cryptography as well as, your time crystal again. So I think general education and reading these non-technical papers, like in Forbes or in science magazines, because they actually have to drill it down for common people. And once you understand that, then you go back to research paper, then everything starts to make sense, is only thing I can say currently.
Okay, great.
I thank you, but I just see it's a Zoom caller. What's your name, please?
My name is Sam, and I've been coming to your seminar. I'm a student at Oxford University. I know Helen from the Kitty's quantum computing stuff. Okay. And thank you.
Yeah, I'll be in touch with you. I'll send an email through to
Great,
Helen.
thank you.
I will get I'll have some questions.
Sure, thank you.
Thanks.
Actually, I have a question. You mentioned during the daytime, the satellite signal cannot be received. So how to solve this problem?
The groups, there are so many groups who are working on that. They are able, like in China in 2020, I guess, they did achieve some sort of they achieved decent rates, I will say, at 1550 nanometers on a free space link. It was not from satellite, but it was rather a free space. And the reason for satellite daytime operation It's because of the background noise on the photons in the outer space coming down, because as like by itself, there's a beam wandering of photons, like even in the nighttime, because of the change in refractive index and all in the atmosphere. But there are work going on. There are so many, like people have suggested using special light modulators along with like a very sophisticated machine learning code to compensate for phase mismatching due to sunlight. So there is work going on. So there might be a possibility in the future to achieve satellite based quantum link during the day.
Or how about using the sunlight itself as a communication medium?
Yeah, that's a good way
That's my
direction to
immediate
go.
thing.
Yeah, actually, the Air Force Research Lab did that. I mean, the daytime quantum link, they already done that. If you search for the Air Force Research Lab, you should see that.
I think there's another question. Can you tell the mission name or paper link for this Chinese work about daytime QKD?
Yeah, I'm looking for that. Give me a second.
Sure.
This one also in Korea, they have done the same thing, but their distance was really small. They did it over, I guess, around 270 meters, the daylight communication. I'll just give you the name of the papers now. So if you search it on Google Scholar, you might be able to find it. I'll just write it in the chat.
Abhi, I mean, sorry, not Abhi, Nitin, I was hoping if you have some moment to talk about what is your plan. I didn't want to take your time earlier. What is your plan for doing? Because at the moment, like you mentioned, that most of the quantum communication that is happening in quantum channel, all the elements, all the identities are pre-established, secured, and you're looking at it, doing it in a zero trust network. So, which means if your satellites are hostile, for example, or your terminals are hostile, how do you intend to do it? Because if you can go in a little bit depth as to how would you first of all establish a baseline, and then how would you go about? What are your ideas? I know there is nothing concrete at the moment, but how do you propose? What are your thoughts currently?
So currently what I'm thinking of, like it might change later on, is to set up a test bed demonstrating like MDI between different buildings, like through a free space link. That is my initial to do thing to achieve the zero trust network. That is what I've been focusing on now.
How to build trust? I mean, how to build trust, and what's your method? You never talk about that. Not
Sorry?
just how to build trust. I mean, it's a zero trust, right? How do you do that? You never say that. I mean, you build real trust, right? What's your algorithm for that?
So using entanglement, swapping, and teleportation, there's one of the solutions to overcoming the trusted issue we have currently in the satellite-based network. So
how the beginning, you don't have anything to trust at all. I mean, so.
Oh, how do you begin it?
Yeah, how do you get identity? I mean, how do you know someone? You don't have no idea, right? I mean, how do you get beginning, very beginning? That's my question.
Okay, that's a good question. Now I have to rethink my approach.
Based on, right, you have something trust, like a blockchain, right? It's idea, but you have some trust issue. You don't just say, oh, I entangle, right? How do you entangle with?
So I think, sorry, David, as you might be already aware, in the classical world, in your regular classical communication, you can actually communicate into a completely hostile zero trust network. And there are a series of steps you have to take. So first of all, obviously you have your normal communication, then you build up your secured landing site, which is your initial channel that will secure the ongoing communication. And then it's a mix and match of trusted computing properties, as well as your your regular Diffie-Hellman key exchange and things like that, your RSA key exchange and things like that.
But
right?
and
I would imagine.
Yeah, that's with quantum computing, right?
So
I don't know why. So for his research, you don't need anything, not anything with his quantum network at all. I mean, just totally other issue, right?
So my understanding would be that initially that we will have to use some of those classical properties in order to tackle into. But then, I mean, if you look at, so one of the things I've been looking at, and this is slightly futuristic, I'm I'm quite interested in this topic. One of the things I'm looking at is, sort of some kind of, how do you describe it? Some kind of spectrographic property of an element that gives its own signature, a unique signature, because every particle emits a type of photon. Now, this is going into physics realm, and I'm trying to lead Nitin into answering some of the questions that I'm trying to ask him. So maybe certain photonic properties that are of a particular device or equipment and blah, 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 for which we can establish that this is the actual party we are speaking to. Then further on, you build up your entanglement, and then you build up your channel on top of that, and then you start your QC. It's something what I'm thinking of. I'm putting out these words here so that when you I did not think about that. Maybe because the question wasn't clear. So that's how perhaps maybe I'm thinking of. What would you say, Nitin or David?
I guess you're saying it right as well, because I read a paper, it was based on quantum blockchain, right? And they had a key agreement before the round in which they do the actual mining to determine whether the person in the group can be trusted or not.
Yeah, I guess you need to go to classic equation, understand what's the zero proof means. Right? I'm not sure you understand that concept of zero proof means, communication means. So that's my question here. So go back to the what's your background? Is it computer science or your background is physics? Yeah. So I guess the good idea suggestion for just go back, take computer science course, equation course, cybersecurity course. Make sure you understand the concepts, because you got to confuse. I'm concerned you confuse the idea from physics side, come to the communication computing side. So that's a totally different story. So you don't solve the zero trustworthy communication at all. You just do your quantum networking side. So just make sure you have the right concept.
Thank you for pointing it out, David.
My apologies. Is Nitish, right? Sorry, I've been calling you Nitin. My apology. I really apologize.
No
Sorry for that.
Sorry, I'm not trying to be rushed. I mean, basically, someone will ask you the question if you got confused. I mean, your paper, right? Yeah, people. I mean, you imagine you have published your paper, right? There's someone got a review, maybe look at, that's not right way to say things. Yeah.
I appreciate it. Like that's.
I'm not trying to bad. I'm just kind of making.
No.
Yeah.
It's like
sorry for that. If I try to be rushed, I mean, we are talking, right? So it's basically before you publish your paper, make sure you got everything.
Yeah. Sure. Thanks.
Okay. Do we have any more questions? I don't see more questions on our chat, so I think that we can finish. Alan, what do you think?
Yes, thanks to speaker again, and then maybe hopefully you can come back again, when you have more things to talk about next year or in future. So we can call it off, and you can, I mean, everybody can see the website, and we have a lot of good talks in November and December also. So check it out, our Washington, quantum computing. Thanks for coming, everybody.
Can we put something on the Washington DC quantum meetup on the LinkedIn? Seems over there is really simple. Make sure more information there, so people can look for it. And maybe some his slides. I'm not sure. We'll put it in the LinkedIn. That'd be great.
Yes, actually, I create a LinkedIn group, Washington DC Quantum Computing. You can follow it, or you can email me. I can put my email.
No, what I mean here, you put. I was there. I mean, LinkedIn meetup. I want to make sure more information there so people can follow. I mean, over there not really simple. I make sure put more information so people can talk to each other over there. That'd be better.
Oh, you mean you want the topic?
No, I want to make sure there's a LinkedIn group. There's more information there. I mean, now we have made our meetup. I want to make sure that actually people can exchange information besides just follow the talk now. Maybe exchange information afterwards, not just during this time.
Yes, you can follow our group on LinkedIn.
Okay.
Yes, you can email me for the link of the LinkedIn.
Okay, thanks.
Welcome.
Thank you so much, everyone, for the questions and possibly the direction I might take for research and further, and for the opportunity for providing me with such an opportunity.
Yeah, good luck. Good luck with the research.
Thank you. Thank you, everyone.
Thank you.
Great stuff, Nitesh. Thank you.